All right, here we go into writing the third degree Taylor polynomial for f of x equals cosine x about something other than 0. So here we cannot use the Maclaurin definition of cosine, unfortunately. What we do need to do is generate this from our original Taylor series. We'll start out there. And remember, we're centering everything about x equal to pi over 6. More on that a little bit graphically. So what I like to do is I like to expand out the general form. That's going to be f of c, which would be f of pi over 6 in this case, plus f prime of c, all over 1 factorial, times x minus c, plus, and then that's going to be, let's see, f double prime of c, all over 2 factorial, times x minus c to the second, plus we want the third degree, so I'll go out to the third degree, f triple prime at c, all over 3 factorial times x minus c. So this is your c value. So we're literally going to do f of pi over 6, f prime of pi over 6, x minus pi over 6, f double prime of pi over 6, x minus pi over 6, and so on and so forth. So as we did before, we are going to write out our bank. So I've got f nth derivative of x, and then f of the nth derivative with pi over 6 plugged in, right, which would be the nth derivative at c. And so in this case, we've got, well, f of x is equal to cosine. That's our original function. We've got f prime of x is equal to minus sine x. Not bad. We've got f double prime. I just wrote 3 there. F double prime is equal to minus cosine x. And last but certainly not least, f triple prime of x is equal to sine of x. Now, whereas we understand that the series for cosine alternates and seems to skip degrees, that's only when it's centered about x equal to 0, because every other term goes to 0. You'll have a sine value in there, and sine of 0 is 0. Whereas here, pi over 6, we get values every time. They're going to be gnarly. So I've got the cosine of pi over 6. So I plug in pi over 6 into cosine. That's equal to root 3 over 2. Gotta know your unit circle. Then f prime of pi over 6. That is equal to minus sine of pi over 6, which is negative 1/2. F double prime of pi over 6. Negative cosine of pi over 6 is equal to negative root 3 over 2. And last but definitely not least, f triple prime of pi over 6 is sine of pi over 6, which is equal to 1/2. And now what we're going to do is plug it into each of these terms, and we'll have our polynomial. So p sub 3 of x is equal to root 3 over 2 is f of c. Done. That first term is easy. This next one is going to be minus 1/2 is going to go up there. So minus 1/2 all over 1 factorial times x minus c, which would be x minus pi over 6. Nice. The next term is going to be minus root 3 over 2. That goes into here. So minus root 3 over 2 all over 2 factorial times x minus pi over 6 squared. And hopefully we can fit this in here. You know what I'll do? I'm going to, through the power of a little bit of, oh, it's not going to let me do it. Let's see if it lets me do it. Yep, I'm going to move all this stuff over a little bit, give us a little more room. And we finally have 1/2 plus 1/2. And that 1/2 I'm going to put up for f triple prime, of course. So that's 1/2 all over 3 factorial, just inserting it here, times x minus c to the third, x minus pi over 6 to the third. And some people like to simplify that down. I'll do that here just to neaten it up. Root 3 over 2 minus, that's 1 over 2 times x minus pi over 6. On the BC exam, leave that. There's no need to simplify it like I'm doing it here. Minus root 3, I'll do that as 2 times 2 factorial. That 2 comes downstairs. X minus pi over 6 to the second. Plus, and then we've got 1 over 2 times 3 factorial times x minus pi over 6 cubed. And that is your third degree Taylor approximation for cosine of x about x equals pi over 6. And I like to think of this as I build each term, it, for some people, helps them to think, now I'm fitting a tangent line to the curve. Now I'm fitting a tangent parabola and then a tangent cubic. Other people, they just like going through the process. All right, let's see graphically what we just did. So graphically, we went through, and this would be like if you have your tangent line approximation at pi over 6. Then we had our tangent parabola at pi over 6. And then our tangent cubic. As you can see, it goes down and then dips back up. This right here is an okay approximation, but it's pretty far off. This, not quite bending to it nicely over here, but pretty well over there. This bends to it nicely on both sides, but unfortunately doesn't curve back up at quite the same rate. The farther out we go, the better off our approximations will get. It's pretty cool. I think that's wicked, wicked awesome. Alrighty then, so let's go on to the next bit. Not so fast. Giving you a little teaser. In the next video, I'm going to go over why do Taylor polynomials work? Why does the process work? I'll see you there in a little bit. Peace.